Hello everyone, my name is Gabriel, Gerrard, Anak, Tagong, and we are from lecture group 2, and we'll be presenting on the software economics project on smart city parking system. So let's move on to the introduction part. All right, so for this project, we use the E3 value model to map out and analyze the economic viability of a digital parking system. And it evaluates on how value exchange between the three primary ecosystem actors, which is the citizen, the city council, and the app developer. And after the completion of the E3 value model, the profitability analysis is conducted using a table and then elaborated. So to conclude the project, we also do robust testing on the E3 value model and based on the 5 scenarios given from the project question. Moving on to the actor populations. So as shown in this table, our ecosystem consists of one app developer enterprise, one city council authority, and for our baseline and upcoming scenario testing, we have used a transaction volume that includes 500 occurrence of general citizens and 500 occurrence of senior citizens, which combines into 1,000 occurrence of citizens. We also account for the local businesses and secondary citizen to test the robustness of the system later on the scenario analysis. Besides that, we also have set a baseline fixed expenses for two actors, which is the first one, the app developer, which has an expense of 300 for the operating cost of the app, and city council, which has an expense of 100 ringgit, which is to maintain the public spaces and the parking space. So let's start with the base model of the smart city parking system. So if we look at the base model, we have set a baseline of 1,000 total parking transaction occurrence. And so firstly, the citizen would send a digital parking fee, which we set to RM, an average of RM 2 ringgit to the app developer. And in return, the developer would issue a digital parking authorization, which allows them to park at said parking space legally. And secondly, because the app utilizes public infrastructure, every transaction would also trigger a secondary exchange, where the app developer would pay a certain amount of commission, which we set as 20% of the total value earned from the parking fees to the city council. And in return, the city council will provide the collection service, which represents the physical parking base, the public space, and also the legal reinforcement framework. So we've seen the base model of our system. Let's look at the profitability analysis table. So if we look at the table, it's pretty straightforward. The citizen has a net negative transaction value, which is negative 2,000 ringgit, which is expected because they have to pay the parking fee to the app developer. And besides that, the app developer would have a positive net transactional value of 1,500 ringgit, which also adds on from the deduction from the expenses from the above table. And also the city council will also gain a 300 ringgit from the 20% commission free from the 2,000 ringgit, which is roughly the 400 ringgit basically. But after deduction of 100 ringgit, it will be 300 ringgit. So let's move on to the explanation on the table part. So as I said, in the base model, we assume an average parking fee of 2 ringgit per occurrence, which generates a total transaction value of RM 2,000. And this is how it's distributed. So for the citizen, they experience a net financial outflow of negative 2,000 ringgit. It might sound unsustainable because it's a negative, but it's quite sustainable because they receive a massive non-monetary value in terms of they save time and effort by replacing the traditional physical scratch coupons or the coupons from back then where they used to set for their parking space. Now it is replaced with the seamless mobile app payments. Now moving on to the second actor, which is the app developer, they collect the raw 2,000 transaction value, and the app developer would then pay a commission fee of 20% from the parking fees which is RM400 to the city council for the right to operate on the public space of the parking base. And also, after deducting their flat 300 ringgit for operating expenses, it will comes to 1,300 ringgit, which then the developer will retain the largest net profit share of 1,300 ringgit, as I said. Now, moving on to the last actor of the base model, the city council. The city council captures a passive revenue stream of RM400, but it would deduct 100 ringgit for the physical maintenance of the public spaces or the parking base, which would net them a 300 ringgit profit or revenue stream, which is highly profitable for the public sector because by outsourcing the payment infrastructure to their partner, which is the app developer, the council would avoid the overhead costs of maintaining a billing system or the operating cost of a app and so on and so forth. Which, besides, they only need to handle the handle the maintenance of the public space or the parking base. Whew. Sorry, and to conclude, the baseline proves that the core system is highly profitable, quite balanced, and mutually beneficial for all the parties involved. So I will now pass the presentation to my other team members, which is Dylan and Eric, to explain on the scenario analysis for the robust testing of our smart city parking system model.
Hello everyone, my name is Dylan, and now I will continue our presentation with the E3 value diagram analysis. So I will explain how our E3 value diagram changes from scenario to scenario. So let's start with scenario 1, the elderly inclusion. So in this scenario, the city council mandated that the app developer must support elderly easy payment (EEP), where senior citizens can either park for free or get a 50% discount for the parking. So how do we modify our E3 value diagram for this scenario? So in this scenario, we show that how the system handles the discounted parking for the senior citizen. As you can see in the diagram, we divide our citizen into two groups, which is the general citizen and also the senior citizen. But inside the senior citizen group, it will have the an OR fork which divide them into two paths, where 50% of the senior citizen will go to the pot that pay a discounted parking rate of 50% discount, and the other 50% will go down a path for the free parking. And also, instead of using only one starting point, just like the best model, we use two starting points in this scenario, which is the one starting point for the general citizen and the other one for the senior citizen. For the occurrences, we put 500 for the general citizen, and for the senior citizen, we put the occurrences of 500. So basically, among the 500 senior citizens, there will have 250 that pay 50% discount, and the other 250 occurrences will pay for the free parking. And the other connection is still the same as the best model.
For scenario 1, the profitability analysis, general citizen has a total value of negative 1,000, senior citizen has a negative value of 250, app developer has a positive value of 600, and city council has a positive value of 250. As for the analysis, in simpler terms, the network architecture is highly robust as both core and commercial public actors sustain strongly positive net values, which are positive 600 and positive 250 respectively.
Now let's move on to scenario 2, the ghost town. In scenario 2, a new mega mall opened nearby, which caused a 40% drop in parking. Visually, all the connection, ports and line between our actors stay exactly the same as scenario 1. The only changes here is in our diagram is the property of the start trigger, which is the occurrences. Our original occurrences is 500, so as there is a 40% drop in the parking, so we change the occurrences value to 300 for each of the citizen, which is for general citizen, the occurrences drop from 500 drop to 300, and also for the senior citizen, the occurrences drop from 500 to 302. So this easily stimulates how a drop in traffic automatically reduces the cash flowing to the developer and the city council.
For scenario 2, the profitability analysis, general citizen has a total value of negative 600, senior citizen has a negative value of 150, app developer has a positive value of 240, and city council has a positive value of 110. As for the analysis, due to the 40% reduction state leading to 600 total transactions, both actors managed to stay in the green, but the scenario proves how vulnerable a fixed expense business model is to market anomalies. For either actors NPV to turn completely negative, transaction volume does not need to hit zero. It only needs to drop low enough that the incoming commission revenue falls below their respective fixed operating baselines.
Next, scenario 3, the data monetization pivot. The app developer decide to stop charging the city council a commission. Instead, they sell anonymized traffic data to local business for targeted advertising. In this scenario, it shows a major business pivot. In our diagram, we made two main changes. First, we completely removed the commission loop between the app developer to the city council. How do we do this? So, we changed the solid line of the value exchange from app developer to city council to a dash line. So this means there is no money exchange there. And secondly, we introduced a brand new actor, which is the local business, with a new value interface. So the local business is connected to the app developer, and the valuation there is 0.4, which means the 40% of the commission, same as the city council just now. But in this scenario, there will be no commission for city council. So now the app developer sell anonymized traffic data to this business, creating a new way to make money without relying on cars parking. So this means the app developer will have two sources of income, one from the general citizen, one from the citizen parking, and the other one from the local business.
For scenario 3, the profitability analysis, general citizen has a negative value of 1,000, senior citizen has a total value of negative 250, app developer has a total value of positive 1,001.3 thousand, city council has a negative value of 100, and local businesses has a total value of negative 350. As for the analysis, in simple terms, the data monetization As for the analysis, while this data monetization pivot makes the app developer exceptionally robust, it breaks the core smart city principle of reciprocity. While this data monetization pivot makes the app developer exceptionally robust, it breaks the core smart city principle of reciprocity. A public municipality cannot legally or politically justify giving away public real estate to a private vendor for free while absorbing a net loss of 100 to maintain those spaces.
Let's move on to scenario 4, the enforcement failure or the free riding. In this scenario, the LPR, license plate recognition cameras, have a 50% error rate due to heavy rain or poor lighting, which allow many cars to park without the system triggering a payment. So, how do we modify our diagram for this scenario? For this scenario, we adapt our diagram from scenario 1 just now, and in front of the occurrences or the starting point, we put a fraction here to show that there is a 85% success rate of the parking, as there is mentioned just now that there is a 50% failure rate due to the LPR camera error. So let me explain this in our diagram. So at first, inside the citizen there is a occurrences of 500. So when it passes through the fraction, it will multiply with the 85% of the success rate, which means among the 500 citizens, there is only 85% that will success for the parking payment. Same goes to the senior citizen. For the paying senior citizen that will pay 50% of the discount, we also put 85% by using a fraction to show that from the 250 paying citizen, senior citizen, there is 85% success rate of among them that will pay for the discounted parking. And the other floor is still remains the same as the other diagram. So that's the only changes for our each value diagram for this scenario, in which we put two fraction in front of the starting point of the two group of the citizen.
For scenario 4, the profitability analysis, general citizen has a negative value of 850, senior citizen has a total value of negative 212.5, app developer has a total value of positive 450, and city council has a positive value of 212.5 as well. As for the analysis, retake. As for the analysis, retake. As for the analysis, reciprocity in the smart city model is built on a clear essential value. When the LPR hardware fails 50% of the time due to weather interference, the developer fails to deliver that core service. Therefore, making this model unsustainable in the long run despite its positive net values. Retake. For the analysis, reciprocity in the smart city model is built on a clear exchange of value. The city council grants the app developer exclusive access to public real estate under the strict legal assumption that the app developer technology will efficiently capture municipal revenue. When the LPR hardware fails 50% of the time due to weather interference, the developer fails to deliver that core service. A public municipality cannot politically or legally tolerate systemic revenue leakage caused by a provider's faulty hardware, making this model unsustainable in the long run despite its positive net values. Therefore, the City Council may not continue the license to operate of the app developer.
Lastly, scenario 5, the incentive strategy or the smart refund. The City Council introduced a smart refund where if a citizen leaves their parking spot 15 minutes early, they will get a partial credit of the parking fee, and the spot is immediately flagged as available in the app for the next user to park. So to visualize this scenario, we modify many things in our E3 value diagram. So let's start with the first one. Inside the general citizen, we use an OR fork to split the path into two cases. The first case is the general citizen that pay RM2 for the parking fee for 1 hour, and the other case is they pay full price of the parking fee, but they get partial refund of the parking fee as they leave early. Same goes to the senior citizen. We also use an OR fork here to split the paying senior citizen into two cases. First one is they pay full price for the parking fee for 1 hour, and the other one is they leave early. So how does the math work here? So as we mentioned just now, the occurrences we put for the starting point of the general citizen, we put 500. So this means there will be 250 general citizen that pay for the full price at 1 hour, and there will be 250 general citizen that will get the partial refund. Same goes to the senior citizen, as we know just now that as in the initial case of this senior citizen, there is 250 that will pay for the 50% discounted parking, and the other 250 will get the free parking. So from among the 250 paying senior citizen, we will split them into two, which means there is 125 that pay for the full price of the parking for 1 hour, and the other 125 will get the partial refund. So how do we visualize the secondary user that will park at the empty spot if the general and senior citizen that leave early? So here we introduce two new actors. The first one is the secondary general citizen, and the second one is secondary senior citizen. So this secondary citizen will fill the empty spot of the primary citizen that leave earlier just now. As we know that in the general citizen there will be 250 empty spots, as there is 250 general citizen that will leave earlier. So inside the secondary general citizen, we put the occurrences of 250 to fill the 250 parking spot that that have empty just now. Same goes to the secondary senior citizen. We also put the occurrences to 125 to fill in the 125 empty spot for the primary senior citizen that left earlier just now. So, and then it will be connected to the app developer, and the connection is remain the same, where the commission still flow to the city council. But in this case, the revenue for app developer is much higher, as there is 4 source of income for the app developer.
As for scenario 5, the profitability analysis, general citizen has a total value of negative 850. Retake. As for scenario 5, the profitability analysis, general citizen has a total value of negative 875. Senior citizen has a total value of negative 218.75. App developer has a total value of positive 918.75. City council has a positive value of 400. Secondary general citizen has a total value of negative 500, and secondary senior citizen has a total value of negative 125. As for analysis, allowing two drivers to pay for the same spot within 1 hour increases the total net profit value of the network, as it maximizes asset velocity, allowing fixed cost infrastructure to capture multiple streams of revenue without increasing operational expenses.
So, to wrap things up, the adoption of the E3 value for our smart city parking system was very successful. We were able to effectively design our core baseline framework, map out the financial profitability of all actors into a table, and thoroughly test the robustness of our model with the 5 distinct scenarios for the stress test. And that brings our presentation to an end. That's all from us. Thank you.